Imagine a world where artificial intelligence doesn't just learn, it invents. Where AI systems dream up entirely new ways of reasoning, learning, and seeing the world, and then teach those methods back to us. In the race to build better, faster, and more creative AI, human researchers are finding it nearly impossible to keep pace with the speed at which technology moves. Every month brings new advances, new models, and new ideas, but there's a bottleneck: us. This paper introduces a framework called Artificial Superintelligence ARC, and this allows for innovation automated by AI. Specifically, it uses AI to find new neural architectures for AI. It's designed as a fully autonomous system, and in theory, it can do this all by itself without any human intervention. So here's what the framework looks like. They call this a closed evolutionary loop, meaning it can repeat again and again as if it keeps evolving. The framework consists of 4 main components, so let's go over each one. First, we have the researcher component. This is like the creative brain of the system. It comes up with brand new ideas for how to design AI models. And these aren't just small tweaks. It's trying to think of fundamentally new ways to build AI. It learns by referencing this cognition base, which we'll talk about in a second. But basically, it refers to its own past experiments and also by reading and understanding what's already out there. These are basically scientific papers, and this helps it come up with new architectural ideas. Now note that the researcher doesn't just think of ideas, it actually writes out the computer code for these new AI designs, and then it also checks to see if the new idea is truly novel and if the code actually makes sense. So this novelty and validity check helps prevent redundant designs and errors, saving a lot of wasted effort. And now, to be more specific, to create these new designs, it actually picks randomly from the top 10 best performing architectures. This is called the parent architecture, then adds ideas from 4 other examples among the top 50 ideas. So it builds on success while also looking at other good ideas. This process runs over and over again. It's a process of self-evolution. In fact, the whole system runs endlessly, and we'll talk about that later. Anyway, after the researcher comes up with a new and correct idea, they pass it on to the engineer. The engineer takes over and performs a real evaluation of that idea by training the new AI model in a real coding environment. What's truly innovative here is the system's self-review mechanism. Unlike other methods that simply discard ideas that don't work, this new artificial superintelligence ARC system keeps detailed error logs if something goes wrong during training, then assigns the same agent to fix the error and correct its own mistakes. It repairs itself. This prevents promising ideas from being thrown away due to small errors. In addition, it has an automated quality assurance system that also analyzes training logs. If the model is training too slowly, say 2 or 3 times longer than expected, or if the loss appears unusually low, this might indicate a flaw. It then ends the session early and sends the report to the agent for review. This greatly speeds up the research process by avoiding wasted computing resources when hitting a dead end. This whole self-correction part is the key to the system's success. In short, the engineer tests the idea in a real coding environment. You might now wonder, how does it decide what's actually good? In other words, how does it choose the winning ideas? That's more complex than just looking at the top benchmark scores. Instead, they use what's called a fitness score, a combination of quantitative and qualitative metrics. For the quantitative part, they use a smart transformation called the sigmoid function. It gives greater weight to small but important improvements, while limiting extreme values. This step helps prevent the AI from exploiting the system's rewards. In other words, chasing a single metric in an unfair way. For the qualitative part, they use a separate large language model, LLM, acting as an expert evaluator, what they call the LLM judge here. It looks at performance, design complexity, speed, and how new the ideas are compared to previous models. After combining these quantitative and qualitative measures, They produce a fitness score that indicates how good the idea is. This score is then sent to the analyzer component for review. The analyzer component gathers information from the perception base and summarizes experiment results, including the fitness score, performance metrics, and training logs. For collecting existing knowledge, it pulls from the perception base, which contains human knowledge such as concepts, algorithms, and historical contexts from around 100 important research papers from various archives. It also generates insights from the performance of current experiments, including training logs, and examines the designs, meaning other similar ideas the system has produced within its family tree. In simple terms, it compares closely related designs, helping it understand why certain changes work or don't work. It draws from human wisdom, but also learns from its own direct experience. These insights are then archived in the central database, essentially updating its memory, and used to guide the next design cycle for the researcher. This loop continues over and over, depending on how much computing power you put in. Overall, it's a highly advanced feedback loop. Now, all of this is very computationally expensive. This kind of exploration and testing can't just brute force thousands of huge models, because every model idea requires precise testing, which would consume massive amounts of compute. Here's another detail about the system. They use a smart two-phase explore, then verify strategy. Exploration phase, they use smaller models, about 20 million parameters, trained on less data with limited validation samples. These are quick, rough tests to identify promising ideas. Verification phase, only the best candidates are scaled up into larger models, which then go through intensive training and precise testing on bigger data sets. Think of this process as casting a wide net first, then focusing deeply on the best catches. An important thing to know is that, because of limited time and resources, they made the system focus only on a special type of design called linear attention architectures. This type of design is smaller and faster than others. If they tried to test thousands of large and complex designs like GPT or QWEN each time, training and testing would take a very long time. That's why they focused only on linear attention architectures, because they're smaller and faster. In this study, the system was used to carry out 1,773 separate experiments, taking a total of more than 20,000 GPU hours. The results were highly remarkable. The system succeeded in creating 106 new and advanced linear attention designs, outperforming the best current designs. The image shows 1,700 designs generated by the system, arranged in a visual map that illustrates the links and relationship between them, like a family tree. The sequence starts at the top with the original DeltaNet model, a linear attention design originally created by a human. And that's why they referred to the AlphaGo Moment in the title, meaning this system made an unconventional move that marked a turning point, proving that artificial intelligence is not limited to imitating human methods, but can create entirely new approaches and strategies that no one had thought of before. Since then, it has been known as the AlphaGo Moment, symbolizing AI's ability for true creativity. This is the summary of the video in which I talked about this research paper. If the information is correct, it represents a major breakthrough that could bring about a radical change and a significant acceleration in the field of AI innovation. We can expect to see developments emerging faster than what we see today. Share your thoughts in the comments, and I will continue following AI news and tools to share them with you. If you enjoyed the video, don't forget to like, subscribe, and share, and stay tuned for more upcoming content.